What's up, my pre-calc people? In this video, we're going to tackle topic 2.7 out of AP Precalculus over compositions of functions. Now, this is a topic that's also taught in Algebra 2, so a lot of you may already be familiar with it. So hopefully just a quick review over what compositions of functions are, how we could take one function and compose it of another function. We could do this with numbers like 2, 3, -1, but we could also do this with x, meaning actually take a generic analytical function f of x and plug it into another function, g of x, to get, well, a new function. It's the composition. Not too bad. The one thing a lot of kids do wrong in this topic is they mess up the algebra. They actually have a great understanding of compositions, but their mistakes come in some really basic algebra stuff. So be very careful as I go through several different examples in this video that you understand the algebra and you don't make any of those silly mistakes. Now, as always, if you're looking for any extra help, please check out the Ultimate Review Packet for AP Precalculus. It has everything you need to do to prepare for unit tests in class and for the AP exam in May. It's got study guides for every single topic of the entire course. It's got answer keys to those study guides, and those study guides are filled with tons and tons of great AP style practice questions. That way you could review and be practicing for the AP exam at the same time. There's also full-length practice exams and tons of additional practice, free response, and multiple choice to make sure you're ready. All right, without further ado, let's continue talking about compositions of functions. So let's start off with the definition of what we mean when we talk about compositions of functions. So if f and g are functions, the composite function f of g, and that little circle, that little open circle is what we mean of. It's f composed of g. What this does, it maps a set of input values to a set of output values such that the output values of g are used as the input values of f. So you see we're putting g into f. So again, the output values of g are the input values of f. I know it can be a little bit confusing just reading the definitions, but once we start doing some examples, I think it'll make a lot of sense. Now, for this reason, the domain of the composite function is restricted to those input values of g for which the corresponding output value is in the domain of f. Now, what that means is that, if you're at your g of x, right, the function that you're putting into f has its own domain restrictions, those domain restrictions carry over to f. If you can't use it in g, well, then you're certainly not allowed to use it in f of g. So that's it for the definition. Don't let that be too confusing. Let's kind of actually look at what it means in notation-wise. So we have this f of g, and some kids call it fog, right, F-O-G, fog, but it means f of g, f composed of g. So we're literally taking function g and we're plugging it into function f. So actually a better way of writing it without this new symbol is to literally, we all understand function notation, right? So f of x means here comes a function with x in it, right? Or we could say, oh, we want to use an m instead of x, so here comes a function with m. Or we could actually use numbers, right? We could take a function and put 3 into it. So instead of putting another variable or a number 3, we're literally taking another function g of x and plugging it into f of x. Now we could also do it the other way around. We could do g composed of f, and in this case we're literally taking f of x, whatever that function may be, and we're plugging it into g. So again, the function f of x is literally going into g. A little bit confusing, I know, but once we start taking a look at some examples, I really think it'll make a lot of sense. Now, the composition of functions is not commutative. That is, f of g and g of f are typically different functions, right? It's not like multiplication where 2 times 3 and 3 times 2 are the exact same thing. You can do it any order you want. So the order here does matter. They're not always going to be the same. They potentially could be, but not always. And most frequently, they're not the same, which means we don't have that commutative property. So don't think that if you reverse them, you're going to get the exact same answer. All right, now there's lots of different ways you could be presented with problems using compositions of functions. One way is using a giant table like this. So in this table, we have several different inputs, -5, -3, 0, 1, 3, 4, 7. And we have outputs for 2 different functions, g of x and f of x. So for example, if we have an input of 3, the output for g of x would be 13. The output for f of x would be -1. Now we could use a table like this to do lots of simple compositions of functions. So for example, what is f composed of g of 1? So we're literally going to take g of 1, and whatever the output is for g, we're going to plug it into f. So again, what we're going to do is we're going to start on the inside. G of 1 is 7. So now that output of 7 is my input for f, and f of 7 is 39. So my final answer is 39. So sorry about that blunder there, but really, really simple, right? We're starting on the inside, g of 1. G of 1 is 7. So now we have our output of 7, and we're going to use that as our new input for f, which we get 39. All right, let's try another one. Hopefully I won't make a mistake on this one. So f composed of g of 0. So start off with what is g of 0. So if g of 0 is 4, so that is g of 0. But now we're going to take that output of 4 and use it as our input to f, and f of 4 is 6. So 6 is our final answer there. Not too bad. How about another one? F composed of g of negative 3. So first start off with what is g of negative 3. G of negative 3 is right here, negative 5. That output for g is now my input for f. F of negative 5 is 15, and voila, I am done. One more using this kind of table. Check out this one, g composed of g. Don't be freaked out when you see this. So we're going to start off with g of 0. What is g of 0? Well, g of 0 is 4. We're then going to do that output of 4, but we're going to plug it right back into g again, and g of 4 is 16, so we get a final answer of 16 there. So it's a little bit weird, but we can actually compose a function with itself. So we first figure out what g of 0 is, get that output, take that output, plug it into g again. In that case, we get 16. All right, now, as opposed to using tables, we could also use functions, like actual analytical functions. So here are two functions, f and g, and f is a linear function, g is a quadratic function, and let's do f composed of g of 2. Now, the only thing that's different about these problems before the previous ones were at the table is that I'm going to actually have to do some math work to figure out what these values are. But always start inside. What is g of 2? All right, so what is g of 2? So I literally have to take 2 and plug it into g. So that's going to be 2 times 2 squared minus 3 times 2 plus 7. All right, let's do the math real slowly here. 2 squared is 4. 4 times 2 is 8. 3 times 2 is 6. So I have 8 minus 6 plus 7. 8 minus 6 is 2. 2 plus 7 is 9. So I get 9. So again, that was my output for an input into g of 2. So now I'm going to take that output 9 and plug it into f, and I get 3 times 9 minus 5. 3 times 9 is, of course, 27. 27 minus 5 is 22. Sorry for the sloppiness, but there is my final answer. So again, really no different than using the table, but I just have to actually take the time to do the math work to figure out what g of 2 is. Go nice and slow. Get that output, in this case 9. Take that 9, plug it into f to get the final answer. Let's do one more of these. This time we're switching it up. G composed of f of negative 1. So this time I'm going to, again, start on the inside of the parentheses. What is f of negative 1? So this time I'm plugging negative 1 into f. 3 times negative 1 minus 5. That's negative 3 minus 5. And negative 3 minus 5 is, of course, negative 8. Now I'm going to take that output of negative 8 and use it as my input into g. So this one's going to be a little bit more work here, but 2 times negative 8 squared minus 3 times negative 8. Plus 7. Be very, very careful here not to make a mistake with some simple math. So negative 8 squared is a positive 64. So I get 2 times 64. Negative 3 times negative 8 there, or negative 3 or minus 3 times negative 8, however you want to say that. It's going to be a plus 24 plus 7. All right, 2 times 64 is 128 plus 24 plus 7. And listen, if you need to grab a calculator to do that math, that's fine. But hopefully you guys can do that math in your head. Not overly difficult, but you should get 159. So, once again, f of negative 1, got my output of negative 8 by plugging negative 1 to f, then took that output, plugged it into g, and I got 159. Not too bad. All right, another way that we can attack compositions is with graphs and functions. So here's one where we have a graph of f of x, probably some type of quadratic parabola, and then we have a rational function g of x. All right, let's do an example. So what is g composed of f of 0? So once again, the first thing we got to do is figure out what is f of 0, and well, we're going to look at the graph and we're going to have to look it up. So in the graph, f of 0 is right here, negative 3. So I don't have a table, I don't have a function, but I do have a graph, and we could just look for the answer. That's not too bad. So f of 0 is negative 3, and I'm now going to take that output from f and use it as my input into g. That's going to be 12 divided by negative 3 minus 1. 12 divided by negative 4 is negative 3. So there's my final answer of negative 3. Pretty simple, not too bad. Let's do another one with this graphing feature here. So we have G composed of f of 2. So once again, we're going to start with f of 2. And for that, I'm going to have to look at my graph. F of 2 appears to be 0 right here. So I get G composed of 0. So again, the output for f of 2 was 0. That output is now my input. And G of 0 is going to be 12 divided by 0 minus 1. And that's going to be 12 divided by negative 1, which is, of course, negative 12. Again, not too bad. All right, let's see here. Let's do another one here. G composed of f of negative 4. So again, we're going to start with that f of negative 4. F of negative 4 looks to be right here at positive 3. So now that positive 3, that was my output, becomes my input for G. 12 divided by 3 minus 1. 3 minus 1 is 2. 12 divided by 2, everybody knows is 6. Not too bad there. Just take your time. And one more here. This time we're going to switch up the order. So we're in f composed of G of 5. So we got to first start inside the parentheses. What is G of 5? Well, I'm going to have to use my function for that. G of 5 is going to be 12 divided by 5 minus 1. That's 12 divided by 4. 12 divided by 4 is 3. So now that output is now my input. I'm going to plug it into f. F is a graph, so I'm going to have to look this up. F of 3 is 3. So I get a final answer of 3. Not too bad. Hopefully you guys understand it. Whether you're working with tables, graphs, or functions, it's not too bad. It should not take a tremendous amount of work. Now, when analytic representations of the functions f and g are available, an analytical representation of f composed of g can also be constructed by substituting g of x into every instance of x in f. Okay, I know it can be a little bit confusing, but basically what we want to do now is we're not using specific values. We're not using negative 1, 2, 3, 0. We're going to just keep it generic. We're going to keep it x. So all we're trying to say here is if you have the analytical representations of the functions, then you don't necessarily need numbers. Let me explain by looking at an example. So let's go back to these two functions we saw earlier. F is 3x minus 5, and g is defined as 2x squared minus 3x plus 7. No numbers here. No 2, 3, negative 4, none of that. We're just going to leave it as x. We're going to keep it generic here. We're going to figure out what is f composed of g of x. So literally, we're going to take g of x and we're going to plug it into every instance in f. So here is f of x, right? F of x is 3 times something minus 5. But we want to actually take g of x and plug it into f. So wherever we see an x in f, we're going to replace it with a g of x. And what is g of x? Well, we can replace g of x with what it is, 2x squared minus 3x plus 7, all minus 5. So you can literally see how I took g of x and I plugged it into f. Like, right, I took the entire function g of x and I was plugging it into any instance of x in f of x. Okay, it makes a lot of sense, right? Not too bad. Now I just got to do some simple algebra work called distribution. Distribute that 3, we get 6x squared minus 9x plus 21. And then I can now combine the like terms of 21 minus 5. So I get a final answer of 6x squared minus 9x. 21 minus 5 is, of course, 16. So there is my final answer for f composed of g of x, or literally taking g of x, plugging it into f. Not too bad. All right, let's do another one here. Same exact problem. Let's just switch the order. Now we're going to take f and plug it into g. So we're literally going to compose g of f. So here's f of x, and I'm going to plug it into any instance of x, which actually happens twice, in g. So once again, g of x is 2 times something squared minus 3 times something plus 7. That is how g of x is defined. But what we want to do is we want to replace those x's with f of x. We're literally plugging f of x into g. But f of x is 3x minus 5. So we have nice and simple here, not overly complicated. But you could literally see how I took g, which is defined as 2x squared minus 3x plus 7, and I plugged f, 3x minus 5, into it. So you could literally see how I took f, 3x minus 5, and put it into g. Hopefully you understand that and see it. Now, this is where we can have the most algebra work. So many kids know the composition of this, but they mess up the simple math work. So we got to be very careful. First, we got to do order of operations. We got to do 3x minus 5 squared. So I'm actually going to come to the side here, do a little bit of dirty work. 3x minus 5 times 3x minus 5. Some kids can do this in their head. I need to do a little dirty work here so I can see it. 9x squared. Negative 30x, get a negative 15x, another negative 15x, makes a negative 30x in the middle, and then a plus 25. Okay, so I have 2 times 9x squared minus 30x plus 25, because I squared that first, minus 3 times the 3x minus 5 plus 7. And now I could do my distribution, order of operations here next, multiply across those parentheses. So I get 18x squared minus 60x plus 50. Minus 9x squared. Whoa, not 9x squared. Sorry about that. Just 9x. Be very careful. Could have been a costly mistake there. Plus 15 plus 7. Be very careful. So many kids know how to do compositions, but they do a problem like this and they really mess up the algebra. So really, really take your time. So combining all my like terms, I got 18x squared. I got negative 69x. I got 50 plus 15 plus 7. 50 and 15 is 65. 65 plus 7 is 72, I believe. So there's my final answer for what we do is G composed of f of x. And notice, as we said earlier, when we do G composed of f and f composed of G, we get different things. The commutative property doesn't hold true. They're not the exact same. It's not multiplication here where, 2 times 3 is the same thing as 3 times 2. We definitely got different things. Here we composed f of G, and here we composed G of f, and we definitely got very different answers. Now, functions given analytically can often be decomposed into less complicated functions. When properly decomposed, the variable in one function should replace each instance of the function with which it was composed. Okay, basically a confusing way of saying, let's work backwards here. So what if we have a function and we want to figure out, hey, are there really 2 functions that were composed of each other to build that new function? And for the most part, these are actually pretty easy to recognize. No one's ever going to give you one that's super difficult. But here's a really simple one. So we have h of x, which is 2 times x plus 3 squared minus 8. So you could say, well, wait a minute. I can actually break this apart. Let's say we have g of x is x plus 3, and f of x is 2x squared minus 8. So you can actually see how I take x plus 3, all right? That's my inside function that went into f. So if I do f composed of g, I'm literally taking g, x plus 3, and plugging it into f, 2x squared minus 8, and that would yield 2 times x plus 3 squared minus 8. Not too bad, right? Should make a little bit of sense. I know this can be a little bit confusing. Now, let's kind of talk about this real quick in a really simple sense. Like, let's take this function right here. I'm going to make this so easy. 4x plus 5. If I said, hey, let's create a function, 2 functions that are composed of each other to build this one. Well, you could just use x, right? You could always use x. You could say g of x is x, like the most basic linear function in the world. And then f of x is 4x plus 5. So we're like, hey, we're going to actually take x and plug it into f of x. But f of x is already composed of x, so if I take x and I plug it in, I'm just going to get the same thing, right? I mean, think about that for a second. F composed of g of x. So g of x is x, and I'm going to plug that into f, which would result in 4x plus 5. The exact same thing. This is actually called the identity function. When you compose a function with another function and it doesn't change, you get the exact same thing you started with. That's the identity function, right? It's like adding 0 with addition. When you add 0, you don't change. 5 plus 0 is still 5. That's the identity when it comes to adding. And multiplying, the identity function is multiplying by 1. 5 times 1 is 5. You're doing an operation, but it doesn't change you. So the same thing here. If I compose a function with x, then I actually get the exact same function I started with, which means that's my identity function. So hopefully that makes a little bit of sense. And let's do one more example of this. So here's k of x, the absolute value of 3x minus 1 plus 4. So you could say that, the 3x minus 1 is my g of x. And I'm literally having f of x be the absolute value of x plus 4. So you could see how I took g, 3x minus 1, and I literally plugged it into f, which resulted in the k, right? K of x, this absolute value of 3x minus 1 plus 4. So a little bit weird, but no one's ever going to try to trick you and make it super hard. And I always tell students, like, if it's not multiple choice, you're just said, hey, I want you to create a function. Just use x, right? Use the identity function, right? That also works. It's silly, but it works, right? Because I could say, hey, if g of x is x, and I'm going to take x and I'm going to plug it into my original function, f of x being absolute value of 3x minus 1 plus 4, then I get k of x, right? I mean, I know that's weird. You might be like, huh? What are you talking about? Well, I try to make it simple, right? If you take x and you plug it in for this x, it doesn't change. That's why it's called the identity function. So composing a function with x is the identity function. It takes you right back to where you started. So you could always do that as well, right? But that's typically not going to happen. These types of problems are usually multiple choice, where they're saying, hey, here is a function k of x. Which two functions composed of each other could create that? And this is where we see this 3x minus 1 plus 4. And let me give you one more example here. Let me give you one more choice you actually have here. You could do something like 3x, right? So g of x could be 3x, and f of x could be the absolute value of x minus 1 plus 4. So again, if you just kind of think about it, if I take g of x, 3x, and I plug it into f for all instances of x, then I would get k of x, the absolute value of 3x minus 1 plus 4. All right, so hopefully that's not too bad. That last part some kids get kind of confused by. We're basically just going we're going in reverse, right? I'm giving you a function and you're creating two functions that could be composed of each other to create that function. It's actually meant to be really, really simple. Hopefully that shouldn't be too hard. But hopefully that was just a really quick, 20-25 minute review of compositions of functions and how we could use tables, graphs, analytical functions, how we could use values, like actual values like 2, 3, 5, -1, or how we could kind of keep it generic with just x's to build our composition function. So the only thing that most kids mess up with is algebra work. So just be very careful you don't mess any of the algebra work up, and you should be totally fine on composing functions of each other.